I have often thought that a good way to look for aliens would be to scan the gamma ray telescope records for gamma rays with an increasing blue shift or a decreasing red shift. When an object is moving toward us, its light is shifted toward the high energy or blue end of the light spectrum. When an object is moving away from us, its light is shifted to the lower end or red end of the light spectrum. This is a basic tenet of relativity as described by Einstein. An increasing redshift would mean the light source is moving away from us and speeding up. Much more interesting, a declining blue shift would mean the light source is moving toward us and slowing down. If, after correcting for the shift due to velocity, the energy of the gamma rays is around 17.6 million electron volts, we would know that a civilization capable of producing a deuterium-tritium fusion rocket was on its way to see us. This would mean they were just a few decades ahead of us, we hope. We would know that their fusion reactors producing deadly high-speed neutrons also, which, you will remember from our course on radiation dangers, is the deadliest form of radiation to living things. If the energy of the gamma rays was 18.3 million electron volts, then they have helium-3 and aneutronic fusion. They would have developed this safer type of fusion and aren't producing deadly neutron radiation. If the energy level were near 511 kiloelectron volts, we can prepare to meet our new masters. This is the energy signature of matter-antimatter reactions, and whoever they are far ahead of us technologically. This is lesson 2 for the course on aneutronic fusion, creating an artificial star. Welcome to the Terran Space Academy. Humanity is at a crossroads. There have been many times throughout our history when it was uncertain that we would survive. If things had gone a little differently, a Neanderthal or a Denisovan, who didn't have to work out nearly as much to stay strong, would be typing something like this, and lamenting the loss of their physically weak but apparently smart ancestral cousins, Homo sapiens sapiens. There is no guarantee that thousands of millennia from now, some other intelligent species from Earth or elsewhere will be looking at the remnants of our civilization and wonder what happened to us. There are many ways we could take ourselves out. A bioweapon that mutates and is unstoppable, making the current pandemic look like a common cold. All-out nuclear war between the United States and Russia or China. Climate shifts that are too severe and too quick to allow enough of us to survive. If we are going to build a civilization that can travel through space and colonize other worlds, giving us a refuge from disaster and allowing our species to satisfy its drive to explore and live free, we must solve our energy problems. Most energy on Earth today is still being produced by the combustion of fossil fuels. These fuels are putting gigatons of carbon dioxide into our atmosphere. Carbon dioxide is a greenhouse gas that traps heat, and our planet is warming as a result. We have crossed the point of no return on the Greenland ice sheets. They will now melt completely, no matter what we do. We cannot conserve our way out of this. Everyone deserves an equal opportunity to live a fulfilled life and have the amenities of what we call the first world. To feed, house, and educate our growing population, we must develop a better way to produce energy. In last week's lesson on the Astrophysics of Fusion, we learned that the strong nuclear force holds nuclei together, but is very short range. Since all nuclei in regular matter have a positive charge from their protons, and the electromagnetic force is long range, like charges repel, and the nuclei are pushed apart. The core of a star has enough pressure and heat to overcome this repulsion, and the strong nuclear force can take over. This is how stars produce energy, through the fusion of lighter elements into heavier ones. These reactions produce a lot of energy. Stars can do this because their incredible mass creates extremely high pressure and temperatures in their core. We can't reproduce this method of fusion energy here on Earth. We can't accumulate that much mass, and it would be hard to fit it into our cars and spaceships. We need a better way. Fusion energy has been the dream of humanity since we figured out that our sun was not a giant ball of gasoline around the turn of the 20th century. We described how protons fuse to diprotons, with one of the protons sometimes decaying into a neutron, creating deuterium. The deuterium will fuse with another proton, making helium-3, which combines with another helium-3 to produce helium-4 and eject 2 protons. This is the only method of fusion readily available to the sun and all stars, early in their lives, because they are made mostly of protons with a little helium-4. Nuclear scientists learned early on that if they wanted to produce fusion, they would have to do it another way. But understand that fusion is not that hard to accomplish in the laboratory. In many ways, fusion was easier than fission. The first particle accelerators were really charged energy particle beams. Strip electrons from an atom, put a large negative charge behind them, and watch the electrons speed away. Put a large positive charge behind your target, and have everything in a vacuum, and you have an effective particle gun. These early guns became the first vacuum tubes when combined with a phosphor screen, and were used in televisions and computer displays for almost half a century. Now let's do the same thing with protons, as Professor Ernest Walton did in April 1932 at the Cavendish Laboratory in Cambridge University. We should all know this man's name, since he was the first to accomplish artificial fission. He used this device to slam protons into lithium atoms, producing fission and creating helium-4, also known as alpha particles, to be produced. Think about this. He artificially turned one element into another, something alchemists had been trying to do for millennia and thought by many scientists at that time to be impossible. But that was not enough of an accomplishment for this laboratory. In the 1920s, theoretical scientists like Einstein, Aston, Eddington, and others had elucidated the process behind the nuclear fusion that powers the stars. Professor Mark Oliphant later decided to fire deuterium, or heavy hydrogen, at a target. This resulted in the formation of tritium and helium-3, both of which he discovered. This was the first example of artificial fusion being accomplished. If fusion was relatively easy way back in the 1930s, then why are we struggling with it today? The terrible difficulty about fusion is not how to do it, but how to make it efficient. How to get more energy out than you have to put in. Why is that so hard? I held back a little in our last discussion. If fusion worked by just slamming particles together hard enough to overcome the electromagnetic repulsion between the positively charged nuclei, the temperature at the core of stars would have to be 40 million Kelvin. But that is not what we observe. Stars are much cooler than that. Einstein had proved that every piece of matter has a probability wave defining its location. Even you. That means that while we may think of things as being in exactly one place, there is an equation that describes the wave pattern of their location. And it is not exact. The particle and you shift in and out of our universe within the limits defined by that probability wave. For something as massive as a person, that shift is less than the diameter of a proton. Imperceptible, but calculable. The radius of a proton, by our best current measurements, is 0.833 femtometers, give or take 0.01 femtometers. Its probability wave is large enough, compared to its size, that it actually shifts in its position by a measurable fraction of its radius. This means that if you put two protons close enough together for a long enough period of time, and the time is very important, there is a chance that they will shift close enough together for the gluons from one proton to latch onto the quarks in the other proton and lock the two together. The two will fuse into a larger nucleus and give off energy. This is a form of quantum tunneling and bypasses the electromagnetic force. This is truly how fusion in stars works. You have to overcome the electromagnetic energy pushing the nuclei apart and get the nuclei close enough to each other, using kinetic energy to cause collisions, and somehow still hold them in close proximity long enough for this quantum tunneling effect to have time to work. So the density of our plasma is one of the most important factors. We have not talked about it, but if you put hydrogen under enough pressure long enough, like in the core of Jupiter, it can form a liquid metal that should be stable. This metallic hydrogen would be the ultimate fuel. Hydrogen is the best rocket fuel, but it has such low density that we need massive tanks. If we could form metallic hydrogen, it would still be liquid, kind of like mercury, but would have a specific impulse of about 1,700 seconds, almost 4 times higher than hydrogen, and the volume would be much less, allowing small single-stage to orbit spacecraft. But it is ridiculously hard to make metallic hydrogen. No one has been able to provably do so yet. But if we could, there is some question as to whether the nuclei and the liquid metal would be close enough together for quantum tunneling to occur, resulting in spontaneous fusion. Until we have metallic hydrogen, we won't know if this is true or not. To create fusion here on Earth, we will need high-density plasma at a high temperature, and some way to hold it all together long enough to allow this tunneling to occur. No material could ever survive these temperatures. The sun holds itself together with gravitational energy, but we do not have mastery of gravity and cannot artificially create gravity fields. But we do have a good understanding and control of the electromagnetic force. If we can create a magnetic field strong enough to contain the plasma and pump energy into the plasma to heat it up using radio waves or microwaves and get a sufficient density at the center and hold it all together long enough, we would have fusion. Scientists tried to do this with magnetic bottles. Static magnetic fields to hold the plasma while it's heated. The problem is that it is easy to hold plasma in a bottle when it's not too hot, but as the temperature rises, the pressure it exerts on that field goes up also. To hold the heated plasma and maintain density, you need a stronger magnetic field, which means bigger magnets, which creates a larger bottle. And then you need an even stronger magnetic field, and you're off to the races. We have been continually chasing stronger magnetic fields and bigger reactors. This has culminated in the monstrosity that is ITER. This is the most massive fusion reactor ever built. The United States, Germany, China, Russia, France, and other nations are making a massive investment of resources to construct this in southern France. It is a tokamak reactor, first designed by the Soviet scientists Igor Tamm and Andrei Sakharov, who had been inspired by the ideas of Oleg Lavrentiev back in the 1950s. The idea here is to make the magnetic bottle a torus or donut shape. We can have the plasma run in a circle around the center of the reactor as we pump in energy to heat it up. Here is one built in the 1980s, still being used for research in the United States and operated by General Atomics in San Diego, California. Here's another from the 1990s. These machines are using powerful superconducting magnetic fields millions of times stronger than what we normally experience here on Earth. These fields are meant to prevent the superhot plasma of the fusion reaction from touching the walls of the chamber. The temperature required to produce fusion is millions of degrees Kelvin. Without the incredible pressure at the heart of our sun, we must heat the plasma to even higher temperatures while maintaining a density capable of allowing fusion. And there is this problem. We've been able to create fusion for decades, but every reactor we build requires more energy to produce the fusion than we get back out of the device in heat. The ITER project is hoping that if we make a massive enough tokamak, we will eventually be able to produce more power than we put in. Now know that this reactor is not a power plant, it is a research facility. If they can accomplish the goal of net energy production, the design will be fine-tuned to produce more efficient and hopefully smaller reactors. The ITER reactor, like most modern tokamaks, does not try to fuse basic hydrogen as protons the way the sun does. There are other isotopes of hydrogen that fuse more easily. ITER will use deuterium and tritium fuel. As we discussed last time, deuterium is a stable type of hydrogen, with a neutron added to the proton. Tritium is the unstable and radioactive isotope of hydrogen with one proton and two neutrons. One of these neutrons will decay into a proton and an electron in beta decay, and the result will be helium-3. The half-life of tritium is 12.5 years, and because it is a radioactive gas, it is somewhat dangerous to work with. It is easier to confine your solid radioactive plutonium than it is a radioactive gas. It turns out that deuterium and tritium can be fused together at lower pressures and temperatures than plain hydrogen. Some reactors have tried to use deuterium and hydrogen, which is also easier than plain hydrogen, and avoids working with the tritium gas, but is not as easy as deuterium and tritium. If this massive machine works, it will be the first continuously functioning net positive fusion reactor ever built on Earth. But I will make a prediction here. It will not work. Not efficiently enough to be worth the expense. It, like the massive space launch system in the U.S., is politically driven job creation and tax absorption masquerading as science. If all the resources, $17 billion to date and climbing for the SLS with a projected operating budget of $2.5 billion per year and $1.6 billion per launch, had been made available to innovative companies like SpaceX, Sierra Nevada, and others, we would have cities on the moon by now. The same thing has happened with fusion. The massive fusion reactor in France will cost us at least $65 billion. 3.9 billion of that from the US and the rest from other nations. If this fund had been made available to innovative small companies, or even a $1 billion prize to the first efficient fusion reactor, I believe we would have fusion now. Let's look at some of these innovative ideas. Now remember, the tokamak has a simple geometry. It is called a toroid and is basically a donut shape. This allows the plasma to run in a continuous circular path and not be held in one place. This simplifies confinement, but any charged particle traveling in a curved path produces photonic radiation. The photons produced by the plasma reduces the energy of the plasma, and this energy must be replaced by pumping photons back in the form of radio waves or microwaves. This reduces the efficiency of the reactor. The smaller the radius, the sharper the turn, and the more energy lost. This is one reason why the scientists at ITER think that its much larger diameter will have a better chance of success. Another thing that makes these tokamaks so difficult is that small areas of instability develop in the plasma and bleed away energy that is needed to sustain the reactions. Scientists at ITER are working to reduce these instabilities with several different technologies, but other scientists think they can reduce or exploit these instabilities to create a different design of fusion reactor. One of these designs is called a Stellarator, which means star maker, a design that hopes to tame these instabilities with advanced geometries rather than size. The Stellarator was developed by American scientist Lyman Spitzer in 1951 at Princeton University, at what became the Princeton Plasma Physics Laboratory. This design, shown here, uses an extremely hard-to-construct twisting geometry to produce a more complicated magnetic field that is more efficient at confining the plasma than a tokamak. Now remember, as we heat the plasma, it tries to expand, but we must maintain a desired density for fusion reactions to occur efficiently enough to break even on energy production. This creates a problem. The hotter the plasma gets, the more energy we have to use to confine it, and then we have to make it even hotter and denser to pay us back the initial energy, causing it to try to expand even more. The Stellarators have been improved over time, and some believe this design will pay off in the end, but it has had decades to work and faces some of the same problems as a tokamak. You have less instability, but you are still radiating energy away on a curved path. The tokamak and the Stellarator are called magnetic confinement fusion. Another good idea is inertial confinement fusion. This idea uses a small pellet of fusion material, usually encased in metal, surrounded by lasers or ion guns, seen here. These devices fire coordinated pulses, collapsing the pellet of fuel, creating shock waves that generate a tiny area of incredible density and heat. Fusion happens, but so far, because instabilities produce high-energy electrons which scatter most of the fuel before it can fuse, these laser and ion guns have not worked well. They are also very expensive and the power requirements are very high. It does not look like this method will be productive. The next good idea is called magnetized target fusion, or MTF. This device is basically a rotating spherical compression chamber surrounded by pistons. The rotation keeps the liquid metal lead and lithium to the sides and allows a channel to form down the axis of rotation. A magnetic field is generated to hold the fuel in the center of the device. The plasma is sent into the center of the chamber through the channel, and an array of pneumatic pistons slam down, sending a shock wave through the rotating liquid lead and lithium, compressing the fuel and causing fusion. The fusion heats the liquid metals, and this heat can be used to generate power, or it would be, if it produced more energy than it takes, but so far it has not. This design has not yet brought the density of the fuel to a viable level. They will have to fuse a much larger fraction of the fuel mass to make this work. The next design is called field reversed configuration, or FRC. It uses magnetic fields to create a toroid of electrical current inside a cylinder of plasma. By reversing the axial field using eddy currents and placing plasma guns at either end, they accelerate two plasma masses into each other and then heat them with particle beams. This design is less prone to instability than other magnetic confinement methods, but so far has not been able to make dense enough stable plasma to break even on energy use. Maybe if they could just make it bigger? Other ideas have been explored also. There is a phenomenon known as sonoluminescence. If you fire sound waves into a liquid, sometimes cavitation will occur where a bubble forms and collapses. The pressure and temperature inside these bubbles can be incredibly high, up to 4,700 degrees Celsius, and plasma is produced. As the bubbles collapse, a shock wave is formed. The pistol shrimp will move its claw fast enough through the water, aimed at its prey, to generate these cavitation bubbles. The resulting shock wave from the bubble's collapse will stun the prey. This technique is being used by the fusion startup First Light, with a metal disc and cube mechanism that is fired into a cavity filled with deuterium tritium fuel. There is fusion, but so far not enough for a net energy gain. And there's another problem. One of the main problems all these fusion reactor designs have in common is that the fusion of hydrogen, deuterium, or deuterium and tritium all produce neutrons. These are high-speed neutrons and, being neutral, are not controlled by magnetic fields. They impact the materials of your reactor, causing erosion and making it radioactive. Is there a better way? If we look back at how fusion in the sun works from our first lecture, you will see the final step is the fusion of 2 helium-3 atoms to produce helium-4 and 2 protons, and no neutrons. This type of fusion is called aneutronic. This would remove the dangerous neutron radiation and reduce the shielding necessary. It would also prevent the erosion and increased radioactivity of our reactor. Can't we just skip down to that step? We could, except that helium-3 is unbelievably rare and expensive on Earth. Remember, it is only created on Earth by the breakdown of tritium, which has a short half-life and has to be manufactured artificially. It wouldn't be worth it. And finally, we get to the helium-3 on the moon, and why it will be the greatest natural resource in human history. Many trillionaires will be created in the upcoming moon rush. Our next course will focus on helium-3 mining and use in fusion reactors for moon colonies, space exploration and colonization, and perhaps back here on Earth. The only resource so valuable that it would be worth the expense of going to the moon to get it and bring it back to Earth. I hope you enjoyed today's course. Thanks for listening. Like and subscribe to help us be able to continue your training for a future in the space industry. Patreon really is coming soon. Stay safe.